History of the Universe and Earth, Part 1. Research by Arpit Borkar. Presentation by Arpit Borkar. Narration by Arpit Borkar once again. And just so you know, my age is 12 years old as of right now. The beginning of the universe. So, in the beginning, nothing was there. Then, boom! The universe, time, and physics got created from the Big Bang, a massive explosion that occurred around 13.8 billion years ago. Yes, time was also created at the same time as the universe itself, so that means that the beginning of the universe was the true year zero. So, shortly after the formation of the universe, it was extremely tiny and hot. Also, the first elementary particles began to form. Elementary particles are subatomic things that are the foundation of everything else. These include quarks, electrons, and photons. However, everything was still very hot, and that meant that nothing could combine with anything else, at least not for too long. Then, almost immediately, the universe started to expand rapidly. From the size of a soccer ball to an asteroid to a galaxy, this rapid acceleration of diameter was likely caused by the separation of the four fundamental forces. Did you know that this expansion of the universe, also known as cosmic inflation, is still happening to this day? Although this expansion of the universe has slowed down considerably. And as we can see, the top image on the right, so that image represents the cosmic inflation. It started out as like very tiny speck, that was the universe, but then started to expand. And the bottom image below that is those are all the type of quarks. There are 6 and they are up, down, charm, strange, top and bottom. The beginning of nuclei formation. Now that the universe's expansion has made it big enough, quarks, electrons, and photons can now roam around more freely. However, the universe is still a big, dense glob of plasma. Also, photons can't make light because everything is simply too scattered for light to be seen. Now, it has been 1 second since the Big Bang has happened, and the temperature of the universe is now cold enough to form protons and neutrons. Particles like protons and neutrons that are made of more than 2 quarks are called hadrons. After 5 minutes, the universe has also cooled down again, so now nucleuses can start being formed. Those protons and neutrons form the nuclei of elements like hydrogen, helium, and lithium. Currently, the universe was made of 75% hydrogen, then 24% helium, and 1% lithium nuclei. However, 15 minutes after the Big Bang, the universe had cooled down to a point where nuclei couldn't be formed anymore. Now, it has been 300,000 years since the Big Bang, and things are getting real. 2 things are happening around this time: recombination and decoupling. Recombination is when electrons can finally start to orbit around nuclei, creating the first ever atoms. So, as we can see in the right, the top 2 images are of proton and neutron. We can see that the proton is made of 2 up quarks and 1 down quark, while as the neutron is made of 1 up quark and 2 down quarks, and they are in groups of 3 each, as you can clearly see. And the bottom is a hydrogen atom. There's a hydrogen nucleus, which is literally just a proton, and an electron orbiting it. At the end of the last slide, we talked about how atoms started to be formed. This is huge. The reason is because instead of a big glob of plasma, the universe is now a bunch of hydrogen and helium gas. How exciting! Secondly, decoupling is when the first ever light could be seen. Because the universe had become much more stable at this point, photons could now be visible. This early light was orange and red, but since then, it has faded and it is now simply microwave radiation. Now the universe is finally a stable clump of gas and light is finally visible. strangely, you wouldn't see anything, as although the light emitted from the photons made it so that the universe wasn't just radio or microwave waves, the early light at the time, which was called the cosmic microwave background, was spread so far and wide that even with extremely sensitive vision, it would only be a faint red and orange fog. Wait a minute, gravity is now starting to take place. Let's go! For this entire time, gravity simply couldn't clump anything together permanently, as the universe was simply too hot and unstable. However, around 300 million years after the Big Bang, gravity started to take very big groups of hydrogen and helium gas, spinning them around at extremely high speeds, and voila, it's a galaxy. Galaxies are basically areas where stars can be made and where stars can die. Dark matter is the foundation for these galaxies, as without them, they would very easily fall apart. Also, that spinning in the early stages of a galaxy, it makes it have a kind of swirly shape. As we can see over here, the image on the right side is actually an image of our very own Milky Way galaxy. How nice! So, how do stars form? Now, you might be wondering, well, how do stars form? Basically, a star forms when comparatively smaller amounts of hydrogen and helium travel towards a specific center point called a core. While this gravitational collapse happens, a bit of spinning occurs as well, making a disc-shaped orbit around the star. We will get to that orbit later. Meanwhile, this exact core is the foundation for a brand new star. Its core goes through nuclear fusion all throughout its lifetime. In short, nuclear fusion means switching hadrons. Over time, the star undergoes nuclear fusion, creating heavier elements such as oxygen, neon, carbon, and finally stopping at iron. After all this nuclear fusion, the star no longer has enough energy to sustain itself and it explodes in an explosion called a supernova. Any heavy materials that were formed inside the star were released through the supernova. These materials either became small asteroids, meteors, or planetesimals, or they mixed with other gases to become liquids such as water. These new liquids either evaporated or froze into ice, as the conditions needed to keep liquid in its liquid state didn't really exist yet. So, usually at the center of a galaxy, a star is born. However, this central star is bigger to begin with and quickly becomes a black hole. This explains why at the center of most, if not all, galaxies, you can see a black hole. Now that the universe can sustain light for a longer time, tiny and faint specks of brightness could be seen. In a galaxy called the Milky Way, a star was born around 4.6 billion years before today. This star is called the Sun. And we can see in the images on the right, the bottom right image is, that star called the Sun. It will be prevalent very much later on, and the top right image is a diagram of nuclear fusion. The formation of the solar system's planets. The Sun, just like many others, made a disk around itself. Anything in this disk, mostly rocks, were bound to the host star's orbit. If they wanted to escape, they would need to acquire a certain speed called the escape velocity. Some of those stones could escape the gravitational pull of our star, but some were bound to it. The closer something was to a star, the hotter it was on average and the quicker it could make a complete orbit. Slowly, the debris in this protoplanetary disk would collide with each other. Some of these collisions made meteoroids and asteroids smaller, while other collisions made these planetesimals bigger. When a planetesimal crossed a certain size, it earned a new title, a planet. Slowly, planets began forming in this protoplanetary disk. All planets started with a small metal core. Planets that were farther from the Sun collected a lot of gas and frozen liquids, becoming gas and ice giants. However, planets that were closer to the Sun only accumulated more rock. Then, at a certain size, all of those planet cores started to melt. Due to the gravitational pressure being higher at the center, some planet cores melted less than others, such as the gas and ice giants, whose cores didn't melt as much as the rocky planets. So as we can see on the right, the top right image is a diagram of Earth in layers, and the bottom right image is what this protoplanetary disk would have looked like. The star at the center and Dust and dirt all around it in a ring shape. The order of the planets. The first ever planet to form was a gas giant, and it is called Jupiter. Because it formed the earliest, it is also the largest planet in our solar system. Our solar system, along with many others, is called a planetary system. Slowly, other planets started being formed until the number of planets in our solar system peaked at around 4.53 billion years ago, when there were 10 planets, 8 regular ones, a Mars-sized terrestrial planet called Theia, and a Uranus-sized planet between Saturn and Uranus, usually called the fifth giant. However, Theia and the fifth giant would be removed from the solar system through different ways. The first one to go would be Theia, colliding into a small terrestrial planet called Earth around 4.51 billion years ago. It is also worth noting that rocky and terrestrial planet mean the same thing. This collision resulted in a bunch of stone debris breaking apart from Earth. All this debris would eventually come together and form the Moon, a small planetesimal called a natural satellite, which orbited around Earth. The Moon started to, like I said, orbit around the Earth after it was formed, and the next one to leave would be the fifth giant. As around 4.49 billion years ago, the fifth giant might have been blown out of its orbit, eventually leaving the solar system. And as we can see on the right side images, the top right one is an image of Jupiter, the first planet to form, and the second image is a representation of what it would have looked like when Theia and Earth collided. The beginning of life. When the Earth was formed, it was just a spherical rock with lava rivers. That's because in the beginning, water wasn't present naturally and it was just too hot. Luckily, our planet was formed in the habitable zone. This means that Earth would neither be too hot nor be too cold for liquid water. Then, a lot of meteors continuously crashed into Earth. This long asteroid shower was called the Late Heavy Bombardment. Some of those meteors had frozen water in them. While Earth was in the optimal area for sustaining life, it was currently blazing with magma, so all the water that reached Earth at that time immediately turned into steam, creating clouds. Those clouds then rained down liquid water, creating oceans, which would be the place where life would develop. Additionally, some of the rocks that made up Earth also contained water that was now being released into the ocean. After the Earth was covered in water, in both at the bottom of the ocean and on volcanic islands from underground volcanoes, ocean water mixed with dust, specks of dirt, and minerals. Some of those chemicals reacted to form amino acids. Amino acids are molecules that make up proteins, one of the basic components of an organism. The leading theory is that these amino acids, along with other molecules, created the first microorganisms. Yay! So as we can see, the top right image is a representation of what the late heavy bombardment would have looked like, and the bottom right image is a diagram of an amino acid. The first era, microorganisms. These microorganisms are called prokaryotes, and they are one of the first life forms on Earth. This is referring to then the last slide we talked about how amino acids started to form microorganisms, the first forms of life on Earth. They were single-cellular, and prokaryotes reproduced asexually, which means that one cell divided into 2, then 4, then 8, and so on. These cells had a very basic structure which included ribosomes, the DNA, flagellum, pilus, the plasma membrane, cytoplasm, and a few other parts. These cells would eat a mixture of minerals until they gained the ability to do photosynthesis, which basically means absorbing sunlight and turning it into energy, specifically glucose. Then, the prokaryotes evolved into eukaryotes. Eukaryotes had relatively the same stuff that a prokaryotic cell would have, including a nucleus, mitochondria, lysosomes, a Golgi apparatus, and additional parts. Along with asexual reproduction, these eukaryotic cells also adopted sexual reproduction, which basically means you know what. Later, these microorganisms would start all of life as we know it, including humans. It is also worth noting that viruses could have likely originated from many of the same chemicals and molecules that make up prokaryotes, although the true origin of viruses is still a mystery. as we can see on the right, the top right image is a diagram of a eukaryotic cell, and the bottom right image is a diagram of what asexual reproduction looks like. So yeah, thank you for watching. As you could see from the title slide, my video right now is actually just a part 1. Part 2 and later on parts are going to come later. So if you want to encourage me to make them, please subscribe and share this video with your friends so they can see it as well. Bye.